This is the beginning of a series of video lectures on polynomials. We'll get into remainder theorems, we'll get into finding their zeros or their roots, etc., etc. In this video, we're going to look at their properties, kind of an introductory video lecture. Our objective is fairly straightforward: identify polynomial functions and their degree. Okay, first things first, what is a polynomial? Well, poly, the prefix poly means many. The suffix nomial means name normally. In this case, it means term, mathematics. So, a polynomial is an expression of one or more terms, many terms, especially the sum of several terms that contain different powers of the same variable. We'll speak to this second piece here in just a moment. Here are examples of polynomials. 3x is a polynomial. Okay, it's a one-term polynomial, so it's also called or also known as a monomial. Okay. X squared minus 2, well, we know that's a quadratic. We know that it has two terms. X squared is one term, negative 2 is the constant term. It's also called a binomial if it has two terms. This just also happens to, the two terms happen to be the highest power of squared, so it's also a quadratic. Here's another binomial that's also a polynomial, negative 6a squared minus 1/2 b. Okay, here's another example of a quadratic, but for our purposes, it's a three-term polynomial. A three-term polynomial is also known as a trinomial. So many of our quadratics are also trinomials, three terms. Here's another one, polynomial. 1, 2, 3, 4, 5 terms. I think there's a special name for a 5-term polynomial. I don't remember it, and nobody ever uses it, so don't worry about it. A constant, like the number 5, is also a polynomial. It's one term, but a polynomial can be just a constant. Okay, now let's talk about this, especially the sum of several terms that contain different powers of the same value. As we're going to talk about, and that'll pull us into what a polynomial function is. Okay, a polynomial function in one variable. We're going to focus the vast majority of our time right here. Okay, so a polynomial function in one variable is a function of the form f of x, that's our function, equals a sub n x to the n plus a sub n minus 1 x to the n minus 1, etc., 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 until you get down to a sub 1 x, or x to the first power, and then finally the constant, which I've written with an x sub 0. Now, of course, x sub 0 is equal to 1. I just wanted you to see the progression of the exponents and the progression of the constant terms, the coefficients, excuse me. So a sub 0 x to the 0 is just a sub 0, and that's just the constant. A lot of mathematical jargon in here. Let's kind of break it down with some examples and some specifics. So first off, it's a function of this form. So what do we know? The a's, a sub n, a sub n minus 1, etc., etc., a sub 1, a sub 0, those are constants. And those are called the coefficients. And we know that. If we look up here, 3 is a coefficient of the x squared term, 1 a coefficient, 1, 1, and then of course the constant is 7. Negative 2, the coefficient of the y squared term. So those are the coefficients of the polynomial. The n's, okay, are integers. Okay, they are integers. These exponents, okay, the exponents are non-negative integers. So a polynomial does not have negative or fractional exponents. They are both non-negative and they are integers. Okay, x is the variable. A sub n, the first coefficient, or the first constant, first coefficient, is called the leading coefficient. N is the degree of the polynomial, so the first exponent, as we write this in order from least to greatest, from greatest to least, is a degree of the polynomial. The monomials that make up a polynomial are called terms. We knew that. So that's a term, that's a term, that's a term, that's a term. Again, look up here to the top. 3x squared is a term, plus y squared is a term, positive x is a term, etc. A sub n, x to the n, is the leading term. That's your leading term, the first one. A sub 0, x to the 0 is called the constant term. Again, you probably won't see people write x to the 0. I just did so you can see the progression. You'll probably just see a sub 0 because x to the 0 power is 1, and so a sub 0 is the constant. The domain of your polynomials is the set of all real numbers, which I've written here in interval notation, negative infinity to infinity. So a lot of stuff you want to keep in mind about polynomials. Let's take a look at some examples. Okay, so here's a polynomial. Example 1. P of x is equal to 5x cubed minus 2x squared minus 9. Okay, leading coefficient, that's 5. Okay, P of x is a polynomial function of degree 3 because that's the largest degree in this polynomial. The three terms, 5x cubed, negative 2x squared, and the constant term is negative 9. The leading term is 5x cubed, and negative 9 is the constant term. Okay, nice time to point out another thing with polynomials is polynomials written in standard form. The polynomial is when the polynomial function is written with the terms with the highest degree first and then descending. So here's an example, example 2. F of x is equal to 3x squared minus 7 plus 4x cubed plus x to the 6th. Okay, in standard form, we want to write the terms with the largest degree first. So I have 4 terms, 1 term, 2 terms, 3 terms, and 4. Largest degree is x to the 6th. The next largest degree is 4x cubed, so I'll write that one second. And then I have 3x squared, I'll write that third. And then in a polynomial, the constant, which is the negative 7, always comes last. Always last. So this is a polynomial of degree 6. Okay, just we'll make a note of that. Polynomial of degree 6. The largest degree is the degree of the polynomial. All right, example 3. G of x equals the square root of x. This is not a polynomial function because the square root of x is written with a fractional exponent as x to the 1/2. The square root of x using an exponent is x to the 1/2, and polynomial functions, as we know, have non-negative integer exponents only. 1/2 is not an integer, it is a fraction. Okay, not an integer. So this is not a polynomial. Example 4. H of x is equal to x squared minus 2 over x cubed minus 1. This is not a polynomial because x squared minus 2 divided by x cubed minus 1 is the same as equal to x squared minus 2 times x cubed minus 1 to the negative first power. Okay, denominator is a denominator is a negative power. Okay, and as we know, polynomial functions have non-negative integer exponents only. That's a negative. So when you see polynomials as a division of two or more of polynomials, it's not a polynomial function. Okay, example 5. F of y equals negative 2y cubed times y minus 1 squared. I did the math, but let's stop right here. Okay, we're going to have to do some math to this in order to see what its degree is, its constant term, etc. So I first expanded y minus 1 squared. Expanded is y minus 1 times y minus 1. And then I multiplied these two first because I felt like it. And I got y squared minus 2y plus 1. And then I multiplied this first term times that. And I got negative 2y to the 5th plus 4y to the 4th minus 2y cubed. And this tells me leading coefficient, negative 2. Okay, it is a polynomial of degree 5. That's the largest degree. So it's a 5th degree polynomial. Okay, how many terms? 1, 2, 3. The leading term, negative 2y to the 5th. And the constant term, we don't write it, but they all have it. In this case, the constant term is 0. Okay, so let's kind of put this together with some stuff we've seen before. Kind of pull this all together with our linear functions and our quadratic functions. So I made a chart here in which I'm talking about the degree, the form, what it looks like as an equation. I guess I could probably write that down. The form or the equation. That might help people a little bit. Then its name and what the graph looks like. Okay, so if it has no degree, okay, that means we're looking at f of x equals 0. That's a no degree function. It's called the 0 function, and the graph is the x-axis. We don't do a whole lot of talking about no degree functions, but that's what we can pull that in because it is the x-axis is a function, f of x equals 0. Okay, a 0 degree function means we're talking about a constant. So f of x equals a constant. A sub 0, remember, is a constant. And of course, it can't be 0 because then we have a no degree. So that it has to be something besides 0. This is a constant function. And this is a horizontal line in the graph with the y-intercept of a sub 0. So draw a graph and then draw a horizontal line right through, for example, f of x equals 6. A horizontal line through 6 on the y-axis. If you go to 1 degree, that means we have an x to the 1, x to the first as our leading term or leading degree. So f of x equals a sub 1. There's a coefficient in front of the x to the first plus the constant. And of course, a sub 1 can't be 0 because then we have a constant function, not a linear function. It's called a linear function. And we know this is a line. It's not going to be horizontal. It's not going to be vertical. So it's a non-horizontal or a non-vertical line with a slope a sub 1, m. We've written that down usually. And a y-intercept of a sub 0. Let's go to degree 2. Okay, it's the equation. F of x equals, well, we need an x squared. So a sub 2 x squared plus a sub 1 x to the first plus a sub 0. And again, you could write x to the 0, but you don't need to. And again, you have to have a non-zero coefficient of your squared term. Otherwise, you have a linear function, not a quadratic function. This graph is a parabola. And we know that the coefficient of the x squared term tells us whether or not it opens up or down. If the coefficient of the x squared term, a sub 2, is greater than 0, it opens down, and if the coefficient, no, excuse me, it opens up. Excuse me, I was misreading my notes here. It opens up if the coefficient is greater than 0. It opens down if the coefficient of the x squared term is less than 0. Okay, one more thing to speak about with parabolas, with polynomials. The graph of every polynomial function is smooth, which means it has no sharp corners or cusps, and it's continuous, which means it has no gaps or holes and can be drawn without lifting your pencil from the paper. So on the left here, this is a graph of a polynomial function. I don't know what its name is. It obviously is beyond a quadratic, but you can see here it's smooth, no holes, no gaps. I can draw it without lifting my pencil. The example on the right has everything possible that makes it not a polynomial function. Here's a corner. A cusp is kind of like a point. You kind of jump up and come down, or go down and come up. Here's a gap. Here's a hole. All kinds of stuff going on here. Any one of these things means it's not a polynomial function. Okay, so you have a corner, you have a cusp, you have to lift your pencil, you have a hole, so not the graph of a polynomial function. Okay, so a lot of stuff there with polynomial functions you're going to need to remember. We're going to get into power functions next, and then we'll get into different things we're going to do with polynomial functions.